the marginals. This is Copula's. So if one can, so this is a multivariate PDF or PMF. This is a multivariate CDF. So we want a wide class of, wider class, wider in the sense beyond normal class of multivariate distributions. For the same reason, we studied so many examples of univariate distribution that given a problem, it's not obvious that it will be a normal distribution. There are lots of different kinds of scenarios, and you might want to use different distributions. We studied like the T distribution, the F distribution, chi-square, and so on. So we want something similar to those, and what we will use for doing that is the tool of Copula's, and what that does it separates the marginal and the joint behavior. So what does that mean? That there is an f which is a function of, say, k variables. So what we will do is we will look at each of the marginals, f of x1, f x1, the first component, x2. So in general what that means is that f xi is you integrate with respect to all the other variables, j not equal to I of the density, joint density dx1 to dxk, but you do not have the ith thing. Okay, so you integrate over all the other things and then you get the marginals. So let's get all those marginals and let's see what is left over after you take out the marginals. So essentially we want to see how the joint behaves if you take out the marginal behaviors, and that function is called the copula. So if you want to do this in mathematical terms, then copula is a function so this function c is called the copula of this function f. And this c, so it's probably not clear why they complicate matters like this. So what happens is these x's, xi take value in R, right, anywhere on the real line. So you have a k dimensional Rk, everything is taking place in Rk. Now where does f1 x1 take value? We have done this as an exercise that if you have a random variable x that follows a distribution f, and if you look at f of x, then that follows a uniform distribution. Remember? Uniform 0, 1. Remember that result? Yeah. So what that means is that these are just in the 0, 1 to the power k. So it's in a small space. Now the problems of like thicker tails and stuff, they vanish once you concentrate only on the 0, 1. There is no tail really. Everything is concentrated on 0, 1. So those things you take care of through the marginal, and then only what is left in the joint behavior you take care through the copula. Okay. So individually, each random variable, each of these directions may have problems, like they may be thick tails, some of them may be asymmetric, some of them may be only positive valued, and so on. So what you do is you don't look at them separately, you take care of all those things through the f, individual f's, individual marginals. And then what C captures is afterwards, how do they jointly behave? If you have uniform 0, 1 random variables. So now all of them marginally are uniform 0, 1, but even then what is their joint behavior? That will be captured by the C. Okay, so that is the function C. So C captures the joint behavior, maybe I have written down, of K uniform 0, 1. So marginally there are uniform 0, 1 random variables. So I should give you some examples and then one theorem. So this is the idea behind a copula. Now we will make this more concrete. So firstly, the definition, what is a copula? So a d-dimensional copula, in this case I use the k dimension, a d-dimensional copula is a function C from 0, 1 to the power d to 0, 1, because ultimately I want to get back a CDF, so the values it will take will be in 0, 1, with the following properties. So I have written down something like this, but does a function like this even exist? Can you actually write f as this? It's not clear. So if you can, what properties will it have and so on. So C u1 to ud is increasing function of each ui.
So dimension of Iiqf and dimension of C are different.
Dimension, they both take value in 0, 1, so they are both scalar valued.
Number of variables.
They're the same. There are k of them, there are k of them.
But C is a dimension of D.
Oh, now I change the k to d. You can keep this as k. So everything you can keep as k. So now I have not even talked about any f yet. I'm just saying that what kind of functions will be called copulas. But we want to construct them in such a way that we get this back. So we have to keep that in mind. So firstly, if it has to be a CDF, if it has to match a CDF, then CDF has this property that for each component you have an increasing function, right? At least non-decreasing. So is maybe non-decreasing. And secondly, if you take all the components to be 1 and this, then what do we really want? Then we want f when each of these f1 of x1 is 1. In particular, this will happen if x1 is infinity, right? Plus infinity. So if we evaluate f at all of these are infinity, and then one of them is such that it is f inverse, say fi inverse of ui, and the others are also infinity. So f of such a thing. So this means that this is the marginal distribution of the ith component. Everything else can be any value. The ith component is less than f inverse ui. So this should be same as the probability of this should be ui. Okay, so this is same as the probability that xi is less than fi inverse of ui. So this is fi of fi inverse ui, which is ui. So this should hold. And thirdly, we must have the rectangular thing. So which the rectangular rule, that you take the probability of a rectangle that should be non-negative. We had that for CDFs. Maybe I should write that down. So C of, difficult. So you have U1 to UK and V1 to VK, and each VI is, say, bigger than UI. So this is U1 V1, U1 V2, U2 V1, U is smaller than V, but no, this is V1. Sorry. U1 V1, U1 U2, sorry, U1 U2. So U1 U2 is this point, V1 V2 is this point. Okay, now we can write down what these are. This is U1 V2 and this is V1 U2. Okay. So this area should be non-negative. So if you take the CDF up to here, you subtract the CDF up to here, subtract this and add this. Remember that kind of inequality? That should hold. So minus 1 to the power I1 plus, so this is a concrete way of writing this, C at W J1 to WJD, and then you sum up. Okay. IK is 1 and 2, and all these sums I1 is 1 and 2, where the W is UJ and WJ2 is VJ. Okay. For all J from 1 through T. So this is just writing this concept for D dimensions mathematically, that you take the Copula function at all the V's, and then you make one of them U, and then you make two of them U, and so on, and accordingly there will be a minus 1 to the power however many you are making U's. So this is the way of writing that thing. But what I have in mind is the rectangular inequality should be satisfied. And again, that you see that because you want to match it to a CDF.
This I1, I2, IK, what limit is in the summation?
The I's are all one or two, either 1 or 2. So 1 would mean that it is the U, 2 would mean it is the V.
Representation of that.
Yeah, representation of that thing with U's and V's in a multi-dimensional case. Yeah, so but it's not necessary that you remember such things, that as long as you understand that it means that the rectangular rule holds, that the probability of any rectangle is I didn't say this, is non-negative. Okay, so these are the usual suspects for properties of U, and any function which has these properties will be called a Copula function. The difference of this from the definition of a CDF is that here we had this to be the probability of U, X being, this was the probability Fi of Xi, Fxi at Xi. So this is not anymore. So this is the new thing, so actually if you want to define a CDF in the general way, you would have only these two properties with the range being RK201. So now you have the range being 0, 1 to the power k, and you have this extra thing which plugs down the marginals to uniform 0, 1. So what that means is that Copula function is in particular multivariate CDF on 0, 1 to the power k with uniform 0, 1 marginals. Now what is interesting is called Sklar's theorem, which says that what we wanted actually is true, that if F is a multivariate CDF, is any multivariate CDF, with marginals F1, F2, etc. up to Fk, then there exists a copula C so then there exists a function with all these properties which satisfies f of x1 through xk is C of f1 x1 through fk xk. Conversely, if C is a copula, if you have a copula on the unit square, or C is a copula, and F1, F2 up to Fk are univariate CDFs, then this F defines a multivariate CDF. Then F above, so F, say we call this star, defines is a multivariate CDF with marginals F1 through Fk. So the question is, given a distribution F, how shall we find what the copula is? So we have a CDF F. Now we want what is the corresponding copula function. So the copula function should be same as f of x1 through xk, where u1 is, we will just match these things here, this u1 is f1 of the x1. So if we want to write the copula in terms of the u's, what we will do is replace the x's by the f inverses. So we will write, instead of x1 through xn, we will write this as f. So the marginal of x1, take the inverse function of that at u1, the marginal of x2, inverse function at u2, and so on. Okay. So if we know an f, we can write down what the copula is. Okay, so far I think that is all we need about the definitions of copulas. One interesting thing is, so this I will call theorem 2, is that if you have an increasing function So let's say you have x, a random variable, with some marginals, and copula is Cx. Now we define a new random variable y. So this is a multivariate random variable, is a k-variate. Now yi is some ti of xi. So each component wise we are defining a function. And we call y as this vector y1 through yk. Okay. The theorem is that the copula of y is same as the copula of x. So if you do something to the marginally, this is you're operating marginally. For each x you're doing some operation, it's not for the whole thing. So if you operate marginally, that doesn't affect the joint behavior. And this is not very hard to show. So, sorry? T also needs to be increasing function. So where ti are strictly increasing.